Okay, before we go on to autoregression, I just want to talk a little bit, I want to talk in more detail about regression. So let's start up here. So you can, yeah. So, all right. The mean here, starting here, the mean of a population was treated as a constant, and we showed how to use sample data to estimate or test hypotheses. Okay. In many applications, the mean of a population is not viewed as a constant, but rather as a variable. For example, the mean sale price of residencies sold this year in a large city can be treated as a constant and might be equal to $150,000. So if we just look at all the homes in this region, we could talk about the mean price. However, we might also treat the mean sale price as a variable that depends on the square feet of living space in the residence. For example, the relationship might be like that. The mean sale price equals $30,000 plus $60 times the number of square feet. So basically, this is the idea of regression. And so let's read this. An important consideration in merchandising a product is the amount of money spent on advertising. Suppose you want to model the monthly sales revenue of an appliance store as a function of the monthly advertising expenditure. The first question to be answered is this: do you think that an exact relationship exists between these two variables? That is, do you think it is possible to state the exact monthly sales revenue if the amount spent on advertising is known? So if you know how much company spent on advertising, can you tell exactly what the monthly sales revenue is? No, probably not, right? We think you will agree that this is not possible for several reasons. Sales depends on many variables other than advertising expenditure. For example, time of year, the state of the general economy, inventory, price structure. There are many variables. Even if many variables are included in the model, it is still unlikely that we would be able to predict the monthly sales exactly. There will almost certainly be some variation in monthly sales due strictly to random phenomena. So even if we could sort of identify all the variables that monthly sales depend on, we still say that we still wouldn't be able to predict exactly what monthly sales are. So if you agree with that, then then we would say there will almost certainly be some variation in monthly sales due strictly to random phenomena that cannot be modeled or explained. If we were to construct a model that hypothesized an exact relationship between variables, it would be called a deterministic model. For example, if we believe that monthly sales revenue will be exactly 15 times X, the monthly advertising expenditure, then we could write it like this. And this would be called a deterministic model. And we mentioned this in an earlier video. This represents a deterministic relationship between the variables y and x. It implies that y can always be determined exactly when the value of x is known. There is no allowance for error in this prediction. If, on the other hand, we believe that there will be unexplained variation in monthly sales, perhaps caused by important but unincluded variables or by random phenomena, we discard the deterministic model and use a model that accounts for this random error. This probabilistic model includes both a deterministic component and a random error component. For example, if we hypothesize that the sales y is related to advertising expenditure by y equals 15x, and then we say plus the random error, we are hypothesizing a probabilistic relationship between y and x. Note that the deterministic component of this probabilistic model is 15x. So the deterministic component of the probabilistic model, the deterministic component is 15x. So here we have a picture where if it was deterministic, it would look like this. But on the other hand, we consider it not deterministic, and so we accept the idea that there's some random error off of the deterministic component like that. Figure 9.1b shows a possible set of points for the same values of x when we are using a probabilistic model. Note that the deterministic part of the model, the straight line itself, is the same. Now, however, the inclusion of a random error component allows the monthly sales to vary from this line. Since we know that the sales revenue does vary for a given value of x, the probabilistic model provides a more realistic model for y than does the deterministic model. The general form of probabilistic models would therefore be y equals the deterministic component plus the random error. Now, in terms of what we said before, we were using y hat before, and you might ask, well, is y hat proper to use here in this equation? And you probably would note that it's not, because we're talking about the actual value. It doesn't fall right on the line, and so we do use y instead of y hat here, where y is the variable of interest. We always assume that the mean value of random error equals 0. This is equivalent to assuming that the mean value of y, that is the expected value of y, equals the deterministic component of the model. In other words, if you take the e of the left side up here, and then e of the right side, e is a linear operator, so e of y will be e of the deterministic component plus e of the random error, and the if we assume, and we do assume, that the mean value of the random error is 0, then e of the random error will be 0, so e of y equals the deterministic component. So, and we have also written, using some other notation, y hat equals the deterministic component. So e of y means the same thing as y hat. In this chapter, we present the simplest probabilistic models, the straight line model, which derives its name from the fact that the deterministic portion of the model graphs as a straight line. Fitting this model to a set of data is an example of regression analysis or regression modeling. The elements of the straight line model are summarized in the next box. Pardon me. So this is, we've seen this before. So I don't know if we used beta before, I can't remember. Y equals beta sub 0 plus beta 1 x plus epsilon. Y is the dependent or response variable. X is the independent or predictor variable. E of y equal beta 0 plus beta 1 x is the deterministic component. Epsilon is the random error component. Beta sub 0 is the y-intercept of the line, right? I think that's easy to see. That is the point at which the line intercepts or cuts through the y-axis. Beta 1, the slope, is the slope of the line, right? That is the amount of increase or decrease in the deterministic component of y for every 1 unit increase in x, right? That's what we mean by the slope, right? As you increase x by 1, you get a change in y of beta 1, beta sub 1. In the probabilistic model, the deterministic component is referred to as the line of means. So the deterministic component is referred to as the line of means because the mean of y, e of y, is equal to the straight line component of the model. Okay, note that the Greek symbols beta sub 0 and beta sub 1 respectively represent the y-intercept and the slope of the model. They are population parameters that will be known only if we have access to the entire population of x, y measurements. However, we don't generally have that. Together with a specific value of the independent variable x, they determine the mean value of y, which is, okay, that's The values of beta 0 and beta 1 will be unknown in almost all practical applications, right? We don't know the population parameters. If it comes from the population, we call it a parameter. If it's estimated by way of a sample, we call it a statistic. The value of beta 0 and beta 1 will be unknown in almost all practical applications of regression analysis. The process of developing a model is estimating the unknown parameters and using the model, and that can be viewed as the 5-step procedure shown in the next box. So when we develop the model, we're basically trying to estimate the unknown parameters. That is, we're trying to estimate beta 0 and beta 1. Okay, let me stop here and come back.